Our next speaker is Chong Sun Chu, the director of the TTS, and his title is Holographic Principle for Boundary Conformal Field Theory and Application. Please.
So, this work is done in collaboration with two postdocs in NCTS, Chong Sun Mao and Wu Zhongguo. So the work has appeared in 3 papers, and there are more results which are being written up. So I'm trying to give a overview about what we have been doing and thinking about, and then more results will be reported in the next talk by Roshi. So it's about holography of boundary conformal field theory. So this is the plan of the talk. So I will start with some background, why this problem is interesting, and what people have done in the literature before we work on this. So basically, Tanakayaki has a beautiful proposal about this, but so I will explain this background. And then it turns out this proposal is not completely formulated, so we have to think about some of the issues in this proposal, and then we come up with 2 more complete, actually it's complete now, 2 complete formulation of holography for boundary conformal field theory. So these are the 2. So these are based on different aspects being generalized from Tanakayaki's original proposal. One is based on generalizing the boundary condition he used, and the other one is based on using some, I say non-standard here because there's some kind of a canonical metric people use in the consideration of holography. So it's not really something, but for the expert, this is standard for us. So then I talk about some application, about what you can learn about for boundary conformal field theory using this approach, which otherwise would be complicated or impossible using the standard quantum field theory technique, ended with conclusion and discussion. So I wouldn't assume anyone know about holography or string theory. In fact, you don't really need to know about string theory. Holography is just some general property about what quantum field theory and gravity should be related to each other. So it's based on study of black hole in the 60s and 70s by various people, Hawking, Rubinstein, and in the course of their studies, and people eventually come up with a proposal of holography by Popov. Gravity formulated on a region which with boundary should be dual to a quantum field theory living on that boundary. So this is the basic idea of holography, and this is the only thing I will use. So and then what I mean by a proposal for a holographic principle is just a concrete realization. What gravity theory are we talking about, and what quantum field theory are we talking about, and spelling out the map between the quantum field theory variable and the gravity dynamics. So, of course, we know holography has been studied in string theory. Well, basically, just without knowing much about string theory, this can be understood. Holography has been studied much in the last 20 years. But most of the time, people have studied this for quantum field theory without boundary. But of course, quantum field theory with boundaries are very interesting. A lot of systems in physics has boundary. So, for example, I listed a few here. Casmir effect, we talk about energy, how the vacuum energy of a system in the presence of a boundary, like a conductor, respond to change of the boundary. Like usually you change the separation of the 2 conductors, then you change the mole, and then you change the energy. So that expresses itself in some kind of force between the conductor. Of course, you can do something more general. You can change the shape of the boundary, but this is very complicated to do in quantum field theory. So this is something we can learn, we can actually do with holographic principle. This becomes a geometric problem, and it become very easy. So this is something I would do. Another interesting effect in condensed matter physics, we have the Hall effect and quantum Hall effect. These occur because we have a boundary, and this boundary accumulates charges, for example, Hall effect, and you have a Hall potential. So it's boundary. And topological material, so this is misspelling here. Topological material has no bulk excitation. Interesting physics occur at the edge, at the boundary, and that manifests itself as some kind of a zero mole current on the boundary. So these are very interesting things. Some of these actually can be we are thinking about to move on to also this kind of more interesting system. So the reason why holography is interesting is there are two reasons why. One, if you consider ordinary quantum field theory in the flat space, non-quantitatively, the system is quantum field theory is very complicated. So you may need to use lattice, or you may need to use some non-quantitative technique, but these are limited. So another possibility is to use holography. You formulate the problem as a in terms of gravity, and usually we turn to geometrical problem in terms of weakly coupled gravity. So this become manageable. And another possibility problem is that even if you consider quantitative quantum field theory, if you formulate a quantitative quantum field theory in a non-flat background, right? In this case, for example, in a flat background with a boundary which is arbitrarily shaped, then this becomes very complicated because, as you know, quantum field theory you have a refraction, or depending on the boundary condition, you have the complications of the boundary. So this is again not easy to do in quantum field theory. You can imagine if you want to quantize a theory with some curved boundary, then it's hopeless. Yeah. So even quantitatively, it's not manageable. But holography provides good hope. Yeah. So this is what I mean. So this is motivation. So in this slide, we explain how such a holographic principle can be formulated and well defined. Mostly for boundary conformal field theory, but in general, this technique can be generalized to quantum field theory. And then I will explain some of the applications which we have considered. So one of them is called boundary wild anomaly, trace anomaly. In the presence of boundary is modified. This effect can be computed using the boundary holography, and Casmir effect, which I just mentioned. And then entanglement entropy in the presence of boundary, that's also interesting. Also some new result which we are writing up, and Rosin will talk about more in his talk, about there's some boundary current which actually could be induced when you have you put a magnetic field. What I mean is that usually if you imagine vacuum creation of particle, you create particle, the particle just go back and recombine, and there's no effective, in the end you just get vacuum polarization. But if you have a B field, then the particle will move, positive negative charge will move away, and there's an effective separation of charge. This can manifest itself as a current, so this is interesting. This potentially can be measured also in experiment. So just to be concrete, what do I mean by conformal field theory with boundary? So it's just an ordinary conformal field theory. You introduce boundary, and the boundary is introduced so that you preserve conformal invariance. That's a boundary conformal field theory. You need to impose boundary conditions which give conformal invariance. So these are called conformal invariant boundary conditions. So for example, you get a scalar field on a curved curved background. So you couple to the, you have some conformal coupling. So this C here, determined by this for dimension D. So this is a conformal coupling. And when you introduce a boundary for the manifold, then you need to take care of the boundary contribution from the Richard scalar. So these are well-known called Gibbon-Hawkins boundary term. So this is basically that Gibbon-Hawkins boundary term. K is the extrinsic curvature of your boundary manifold. So basically the Riemannian curvature tensor for the whole space, when you have a boundary, that decomposes into components living on the boundary and then orthogonal component. So the one living on the boundary manifold, these are the intrinsic curvature. The one living in the orthogonal, roughly, these are the extrinsic curvature. Roughly, yeah. So this enter here. So there are two-part boundary conditions you can impose. You just vary this action, and you need variation principle tells you that you have to impose either directly or this. This is just not because you have this additional term like a mass term here. So you get a mixed, you get a Riemann boundary condition with like a mass term here. This is called Riemann boundary condition. The action can be checked. You can check this is a conformal invariant. You change the metric, you scale the metric, then it's exactly conformal invariant. But quantum mechanically, this is no longer a symmetry. So you can measure the violation of the Weyl symmetry by by doing this, by looking at the effective action, not just a classical action. So, and this is the anomaly. So the anomaly is a general feature of any quantum field theory, and it has a local expression as a integral over some curvature invariant on the boundary. So these are well-known feature of quantum field theory. It's connected with index theorem. So without boundary, if M is just a compact manifold, and the trace anomaly, this is called the trace anomaly because you're looking at the trace of energy moment tensor. So this is 0 in odd dimension, everyone know about. In even dimension, is classified in terms of the number of invariant curvature invariant you can write down. So in 4 dimensions, you have something called Euler density. So it's like the ordinary 2-dimensional manifold. You have the Euler number, which is the number of handle, holes, and faces, surfaces. Yeah, you can triangulate the surface. There's a high-dimensional analogy. So these are Euler invariant, and then you have something called the wild invariant, and you have the central charge. So this is a standard form you can derive. The only thing which depend on quantum field theory is that this data C and A is called a central charge. For different theory, you have a different C and different A, but then they're normally factorized into this form. Yeah. But in the presence of boundary, this becomes a bit more interesting. You have also boundary anomaly localized on the boundary. So on the boundary, as I said, you have also boundary curvature invariant because your V1 curvature decomposes into different representation with respect to the boundary. So now in 3 dimension, you have 2 kind of invariant. One is you have the intrinsic curvature, which is scalar, and then the other one is this K is the extrinsic curvature. So you have 2 kinds, and then in 4 dimension, with a 3-dimensional boundary, you have 2 invariants. So these are standard. And again, you factorize, and then you have a boundary. You have coefficient in front. This coefficient in front, depending on the boundary condition, is called the boundary central charge. So one of the things which we would like to do, so these are construct generally using general property of quantum field theory. We would like to reproduce this, at least any orographic principle of boundary conformal field theory should be able to reproduce this. Yeah. So, well, this is just a table people have computed. For free theory, this can be computed. So all these coefficients can be computed. Of course, in interacting theory, this is hopeless. People haven't done anything. Yeah. Maybe simple example. No general table. No. So the proposal of Untitled. What's the proposal? So if you know just a little about ADS CFT, then we know CFT has a dual in terms of ADS space. ADS space, if you just roughly speaking, you can think about ADS space as a hyperbolic space, and then of course it has no boundary. So what the boundary is about? So the boundary is that you introduce some coordinates of ADS, so that you talk about the upper part of ADS and the lower part of ADS. If you talk about the upper part of ADS, so then of course then there's a boundary. This is the boundary of the upper part of ADS, and this is, if you consider gravity in this ADS space, then you have a quantum field theory, you think of the boundary. So we consider ADS space, this is the Poincare coordinate in the upper part, that means z greater than 0. Your quantum field theory will be looking at the boundary defined by this xi here. So xi will be d-dimensional, and this is a d+1 dimensional ADS space. So that was for quantum. So this is basically the quantum field theory, the ADS CFT statement about how one should formulate ADS CFT. All the variation about ADS CFT, for example, we put different CFT. It just corresponds to considering slightly different gravity theory in this space. So the prototype is just you have a quantum field theory defined by some energy momentum tensor, and the dual will be a gravity theory, Einstein gravity theory, for example, you take in this space. If your quantum field theory has a little bit more feature with the current, then your current will couple to some gauge field in the above, and you have to consider some gauge supergravity here, etc. So all the ADS-CFT are basically just based on this geometrical picture of ADS space with the boundary. Now, Tanakayaki in 2011 considered the situation. Your quantum field theory or conformal field theory is not defined on a compact space, but it's space with a boundary. So with a boundary defined P here. So for example, this M, you can say always this is a boundary. Yeah. So this is a boundary conformal field theory. And what should be the dual of this? So it's just say, if you have the whole space, then you have the whole upper part. If you have a part of the whole space, then you should have a part of the ADS space. This is very intuitive. Yeah. So basically, what you need to do is to think of determine this surface like a fish net here. This fish net as a boundary on your boundary conformal field theory. We need to know the shape of this fish net, and in every gravity processes happening in the interior of this cube will be due to the conformal field theory acting on M. So this is the basic idea. So the determination of a Q is the crucial part. So I skipped the derivation, but basically he come up with this equation by doing some variational principle of the gravity action in the presence of boundary, and you have variations like this, where K is the extrinsic curvature of your Q. So Q is a surface, so it's described by some embedding, and then there's come with an extrinsic curvature tensor. K is a trace of that K, and T is just a parameter one introduced in the bulk gravity theory, the free parameter you can check. So this is a second order differential equation because K is basically extrinsic curvature. Extrinsic curvature is like, for example, if a circle, you need to look at not the tangent. The tangent is of course flat, but the variation of tangent to describe curvature. So second derivative. So second derivative equation for the embedding function. So and then with a boundary condition that the boundary is embedding function to give you just a shape of your boundary manifold P. So this is an equation with boundary condition, so it can be solved. So you solve it, for example, for a flat two-dimensional boundary conformal theory. So with a boundary which is flat, what can it be? If you want to take, so this picture here, your boundary conformal theory is living on the negative Z. Q, there's nothing you can be. It can just be just a sheet extending to infinity. Yeah, it cannot come back because this extends to infinity. M extends to infinity. So it's just it can asymmetry. I mean, more or less, it must be just a slope. So you can determine this, and then you solve the equation, and then you find this. Yeah. So rho star is just a reformatization of P, the parameter we introduced. So and then there are also other example one can do. So I will skip. So it's important to understand what's the meaning of T, this parameter T in the theory. So this is what you can do. So entropy, entanglement entropy, for example, we consider a subsystem in this boundary conformal theory of length L. And generically, the entanglement entropy of that will have this piece log L. Yeah. But in the presence of boundary, actually you pick up a term which doesn't scale with L. It's a constant. So the physical picture is just that your system is defined on L, and that's an extensive quantity. So your entropy is scaled with L in this way, in 2 dimensions. Yeah, in high dimension it's extensive, so it should be L to power some power. But in 2 dimensions it turns out to be this. But then there's also a piece which is the entropy concentrated on the boundary local degree of freedom. This is called the boundary entropy. So this is something people know in general from conformal theory. So he was able to reproduce the same form of entropy from his proposal of holography, and then identify the boundary entropy with the computation. So the T or the rho star is interpreted in terms of the G function of the field. So the T introduced is measuring some kind of degree of freedom of the boundary system. Okay. So the problem with this proposal is that we have only one embedding function because Q is a codimension one surface in ADS space. So we have only one embedding function. But the embedding equation in general is a tensor equation. It has too many components. So it cannot be solved. Apart from the simple case like a flat boundary or circular boundary, you have symmetry, so the equation, this set of equation reduces to one equation, and you can solve. So in general, it cannot be solved. That's the starting point, how we enter the problem. We try to resolve this puzzle. So there are two possibilities. The first is based on generalizing the boundary conditions in use. So I mentioned in this simple derivation, he imposed a Neumann boundary condition, basically saying, oh, this boundary derivation of the boundary metric is completely free, so so this matrix should be 0. So you get this equation motion for Q. But you can imagine it's not all of them are free, but only a trace part of that is free, so you get a trace of that equation. So basically, to cut the story short, we have a proposal by instead of looking at the whole set of tensor equations, we look at the trace of that set of tensor equations. Because of diffeomorphism, we want to take the trace. Yeah. Okay, these are technical here. So, and we can solve it. So just believe me, we can solve it, and then we find the embedding. Now, X is the field theory direction, Z is in the buck. In this solution here, previously it was a straight line. I explained to you this just a straight line, nothing else it can be. But if the boundary is longitudinal, it's curved, and of course it can be the surface can be curved, the Q. Yeah, so it will be described by some expansion like this. So now we, in this approach, in this proposal, we can also solve for example, the next coefficient. Of course, you can click on, and it's just a matter of time. Yeah, you can do all of these. So the next one is this. So this previously was equal to 0 because the boundary was considered to be flat. So K was 0. So this is just the first step in working on the proposal. So we have also applied this proposal to, for example, to reconstruct the Wow anomaly and reconstruct all the necessary terms in the Wow anomaly. So this is the second proposal. Second proposal is based on something non-standard. For the expert, the standard ADS-CFT is based on a extension of the ADS metric, which is asymptotically ADS, but you walk into the box, assuming some smoothness condition. That was called FG. So there's a Federman and Graham, two mathematicians, has developed this technique of asymptotic expansion of a metric with an ADS bound metric. So in case of that metric is completely fixed. That's the reason why we cannot solve the embedding equation. But we found that actually there's a non-standard FG expansion in which the metric actually is not completely fixed. There are some additional degree of freedom you can have in the metric. So the price is that you break some of the smoothness in the FG expansion. So this is a bit technical. So I just tell you the metric will be of the solution of the bug will be of this form, and the solution this function has some coefficient which are free now, so which is not available in the FG expansion. Then in that case, then now we can solve this equation without any problem, because you have additional constant, and this additional constant allow you to fix the additional constant in the embedding. And then when you go higher and higher order, you get more and more constant, and which allow you to fix more and more term in the embedding equation. So application, I described 3 applications here. The first is an anomaly. So the boundary Wow anomaly can be computed by looking at the Bach Einstein gravity action. This is the Einstein gravity action with a cosmological constant because it's ADS. And then you have all these boundary terms, which I will not explain. Just because in the presence of boundary, you have also this Bach term. So this term will contribute to your energy moment tensor in the field theory, and then also contribute to the anomaly. So after you do the computation, then you get this for the proposal 1 and this for the proposal 2. So you do get all the expected form of the gravity invariant. The only difference between the two proposals is that you get different expression for the central charges. But they agree when rho equals 0, but in general the functional form are different. Yeah. So this corresponds to different boundary conformal field theory, because boundary conformal field theory can have different configuration of central charge in general. Entropy. So we take a simple example, let's say 2 dimension, and then you consider the entanglement entropy of this system A with a length L, and then compute the boundary entropy. So using the connectivity formula, there are new feature, but I don't explain. So anyway, in any case, you get the final result, which is easy to understand. So there's a critical distance from the endpoint from the boundary. If you're very far away, effectively you don't see that boundary. This is what we find. The entropy, entanglement entropy is the same as if there's no boundary. Okay, but when you get close enough to the boundary, then the theory start to see effect from the boundary, and then you get a different form of the entanglement entropy. So there's some kind of phase transition here. The value is smooth, but the derivative is not smooth here. So this is an interesting dependence of the boundary on the entanglement entropy, and this, in principle, can be observed in experiment. Yeah. I don't know how difficult it is to observe it. The final thing I want to talk about here is that is Casmir effect. So normally, Casmir effect, how do we describe Casmir effect? We need to talk about the energy. Energy is energy momentum tensor. So we need to know basically the behavior of energy momentum tensor near the boundary. So x equal to 0 is a boundary. In a general quantum field theory with boundary, this is the behavior of the energy momentum tensor. In the conformal field theory, this leading term go away and the subleading term dominant. So this here, where k is the exterior extrinsic curvature of the boundary. So this is a geometrical effect. And the coefficient alpha depends on the kind of boundary conformal field theory one consider. Now this, at the first look, this may look problematic because at x equal to 0, you get a divergence in the energy. But this is seems to be unphysical. How can you get an infinite energy? And this has been a problem in the 70s, and then when they first discovered this. But then shortly after, people understood actually this can be normalized away by using a boundary conductor localized at the boundary. In this, then you get a final energy. Yeah. So what I really want to say here is that there are two features interesting. One would like to reproduce using the holographic boundary conformal field theory. One is this behavior near the boundary or the energy momentum tensor. It depends on the extrinsic curvature. And the other one is this boundary conductor, so that the energy is finite. So, so indeed, we do the computation. We find we find both features. Yeah. So we find the expected form of the boundary behavior. So we can compute this coefficient in 3 dimensions and 4 dimensions. And what is surprising is that this coefficient, this we call Casmir coefficient, has a relation with the boundary central charge, which people have not noticed before. And we do this for both proposals, and it's correct. This relation holds for both theory. So although this the boundary central charge depends on the T, the boundary entropy, the G function, but the relation itself is universal. So this is actually has a interpretation. Rosing will explain in his talk. And also we produce a precise surface Hanna term to make the energy finite. So recently we have, as I said, we have extended the discussion of Casmir effect, basically the presence of boundary on the energy momentum tensor to current, and we find interesting effect on this induced current in the presence of external B field. So in that case, it's not because of the leading term is not because of the curvature of the boundary, but it's because of some external H field introduced. So I summarize my talk. Based on original work of Kanadayaki, we have provided two complete proposals for holographic BCFT. One is based on the ordinary FG extension of the Park metric, but using an alternative scalar type equation for the embedding. The other one is a new non-FG extended Park metric, by using his original boundary condition in the original tensor type equation. So both work and both reproduce all the expected features for boundary conformal field theory, including boundary Raoult anomaly, boundary effect on the energy moment tensor in the form of a Casmir effect. Both of them give you the universal relation between central charge and Casmir coefficient, and we have applied this to study new relation for current, which is potentially measurable in experiment. So the proposal can also be applied to other systems. For example, we can look at other questions also. For example, we can look at the geometrical dependence of P energy and boundary entropy. So I just look at the boundary, classical boundary for the entropy, but you can also look at the shape, how the shape change would affect the boundary the entanglement entropy, for example. One can also study Wilson loop. These are things string theory people will be interested in, like integrable systems, spin chain, and how they are affected by boundary effect. For string people, there's a typical boundary conformal field theory, which is hasn't been understood so far, which is the boundary conformal field theory describing the self-dual string. So these are a bit technical. But these are potentially interesting applications of this boundary conformal field theory. So I finished my topic. Thank you.
So, is there any question?
So I have a question. I'm not sure about okay, so I'm sure about the defect CFT is included in these scenarios. I mean, by including the 5 branes in the context of the usual AD surface 5, we can realize the defect conformal field theories. So that is included in this scenario. So then,
As long as it's a BCFT, then.
So then, in that case, actions for the defect CFT, so you can produce DCFT quantities by using the usual techniques. So probably you can explicitly consider the relation to integrals, spin chain.
Check something. For 4-dimensional, or any Fourier mules also, the supersymmetric boundary condition has been classified and understood. So spin chain in any Fourier Fourier mule, of course, is well studied. So I think that would be, apart from the D5, I think for D3 is also an interesting system.
Any more questions? So your proposal 2 is more general than the proposal 1?
No, it's based on different, but because there's one problem about the embedding. So we need to find some way to accommodate the embedding. So in the first way, we take the scalar equation. So we have one embedding equation and one equation, so it can be solved. In the second one, you have still a tensor equation. So let's say you have 2 equations, but you have one embedding function. So this cannot be solved. You have 2 equations on one unknown, it cannot be solved. So we find that in that case, actually the embedding, the equation itself, depending on the Park metric. The Park metric, if it's not fixed, then you can use that to give, to allow you some additional freedom to solve the embedding equation. So for example, in this, I just counted, you have 2 equations, but you have one constant from embedding and then one from the metric, and you can still solve it. So this is what's happening. So it's not more general, it's just 2 different ways you can overcome this problem and have a complete proposal.
So, If there are no more questions, let's thank speaker again. Okay, so the last speaker of this session is Yongjing Miao from CPS, and the title of his talk is Shift Dependence of Casmir Effect from Well-Known in BCFT. So please.